A complex number is basically just a number that can be written as a plus bi, where this a here is just any real number and this number b here is just another real number. So we can kind of just extract the parameter a and b here and write that as an order pair ab. But well, when we have an order pair, that also means we can write this AB, we can think of this AB as a point in the plane. So that means we can think of the complex number just as a point AB in the coordinate here. Or we can also think of this AB as a vector as well. So this complex number can be thought of as just an order pair as a point on the plane, or it can be also think of as a vector AB as well. Now, there is another interpretation of this. Let me talk about, like when we think of real number, we can think of a real line. So a real line, let me actually kind of write this on the side here. When we think of a real line, so this real line is going to have 0, 1, 2, and positive number goes here, and then negative number goes on the other side. This is called a real line. So all the real number that you can think of is going to lie on this line. And you can notice there is no imaginary number here, so no imaginary number is going to be on this real line. But what we can do is, well, we can just add another axis to this. I'm just going to call this the imaginary line. This is imaginary line. And I'm just going to put all the imaginary number on this line here. So I'm going to have I, 2i, and 3i on this side. And I'm going to have negative I, negative 2i, and negative 3i on this side. So here, what that also means is I have now a plane, and whatever complex number that we have is going to lie on this plane. If I have, for example, a plus bi, my a plus bi can be represented as just a point ab here. So the real part is going to be a here. So this a is going to be a real number, and that is represented by the fact that, my complex number is a plus bi. So this a is a real number. So that corresponds to the real number a here. And this bi would correspond to the number b on the imaginary line here. So this bi is going to be somewhere in my imaginary axis. So we can also think of this as a vector as well. So this plane is going to be called the complex plane. So in a way, we kind of extend the real line, the one-dimensional line that we usually think of when we think about the real number to a, no, not a complex line, I mean complex plane. So yeah, we extend the one-dimensional real line to the two-dimensional complex plane here, and we can represent whatever complex number that we have in this plane. But now, whenever we have things in a typical coordinate, that also means we can write that in polar coordinate in a way. Well, if we think of the vector, okay, so let's say I have once again a complex number a plus bi, and we think of them as a vector. I'm just gonna write ab here. Now, we can compute the length of this vector because, I can draw a little triangle underneath this guy here. The length of the base is going to be a, the length of the height is going to be b. So that means the length of my vector, the length of this arrow here, is going to be just the hypotenuse of the triangle here. So that's going to be, by the theorem of Pythagoras, that's going to be the square root of a squared plus b squared. And notice how this is actually just the same as the formula of the norm of the complex number. So this is kind of why the norm of the complex number, it actually has the interpretation in the geometrical sense as well. And now, that means we can also write this complex number in polar form. To write a complex number in polar form, we need to know two things, which is the angle that the vector, the angle between the vector that we have with the positive horizontal axis and the length of the vector, which is the r here. Now I can write this complex number a plus bi as r times cosine theta plus I sine theta, or sometimes I'm just gonna shorthand this to c and the I and the s here as r cis theta. So the complex number a plus bi that we see earlier can also be written in what we call a polar form as r times cosine theta plus I sine theta or r cis theta. But, well, first thing first, why is this two thing equal? So if you actually look closely at the triangle that we have here, so I have the little triangle here. If I want to compute the sine of theta, let's say if I want to compute sine of theta, what am I going to get? Sine of theta is going to be b over r. It's going to be b over r. If I move r to the other side, I'm going to have that b is going to be sine theta times r, sine theta times r. Okay? And if I want to compute cosine of theta, my cosine of theta is going to be, let's see, a over r. Now then, I can move r to the other side, so then my a is going to equal to r times cosine theta. Let me actually write this one as r times sine as well, r times sine theta. So then, that means I have that a is r cosine theta and my b is r sine theta. I can then make a substitute. My a is this guy and my b is this guy. So a plus bi, this is just going to equal to r cosine theta plus r sine theta times I. And we can pull out the r and rearrange that a little bit. So that's how we can arrive at r times cosine theta plus I sine theta here. So let's look at the example that we have down here. I'd like to locate 2 plus 2i in this complex plane. So 2 plus 2i, if I were to extract just the number, I'm gonna get 2, 2. So the coordinate that I'm looking for is gonna be 2, 2, which is right here. So this 2, 2, this 2 plus 2i, I can think of it as just a point here, or I can think of this as a vector as well. So that's how I can represent this complex number 2 plus 2i. Now then, if I want to write this in polar form, I'm gonna need to know two things. I need to know the angle between this vector here and the axis. I need to know this angle. I need to know the length of my arrow here. I need to know the length of this guy. Well, this is not too hard. We can just eyeball that and see that the angle here, this is gonna be just 45 degrees, and the length of this guy, I can use the Pythagorean formula. Once again, this is going to be just the square root of 2 squared plus 2 squared, and that's going to be just the square root of 8. So the polar form for this one is going to be just square root of 8 times cos plus, or let me actually write it in full first. It's going to be just square root of 8 plus cosine of theta plus I sine of theta, where my theta here is going to be just 45 degrees. 45 degrees here. Or we can write this as, well, let me actually write it shorthand. It's going to be square root of 8 plus 6 of 45 degrees. Or we can write this in the radian as well. So 45 degrees in radian, this is going to be pi over 8. Now, one thing I'd like to point out is that the polar form is usually not unique, and this is because the angle here, we can, well, like in the, let me see, in the unit circle, when we have the 45 degree, I can make another rotation. So 45 degrees, this one, I can make another rotation. So 45 degrees, this is actually the same as, let me see, if I add 360 to 45, I'm gonna get 405. So 45 degree and 405 degree is gonna be the same in terms of relative to the unit circle. Or if we have pi over 8, so it's the same angle anyway, so pi over 8 is here. I can go clockwise, so pi over 8 is gonna be just the same as negative, let's see, this is going to be negative 7 pi, oh wait a minute, negative 15 pi over 8, negative 15 pi over 8. So I minus 2 pi. I subtract 2 pi from this guy, I get negative 15 over 8. Yep, so that's right. So, that means I can also write this as square root of 8 cis of 405 degrees. Or I can write this as square root of 8 cis of, negative 15 pi over 8 radian as well. So there are many ways that we can write a complex number in the polar form. Now then, let's go to the next one. I'd like to first find the square root of 3 minus I. Square root of 3 is 1 point something, so it's going to be here, and minus I is going to be here. So the coordinate for this guy, if I were to write, it's going to be square root of 3 and then negative 1, because you know negative I, this is just negative 1I. So then negative 3 minus I is going to be here. Now then, if I were to write this in polar form, we can probably just eyeball this, but let me actually just go back. Wait, let me actually draw a nice arrow. Okay, so let me kind of go back a little bit. Now, how do we write things in polar form? So in polar form, we have to write a plus vi as r cis theta or r cosine theta plus I sine theta. So the two things that we need to find out is the parameter r and parameter theta here. Now r is easy because r is just going to be the length of my vector. So to find r, that's just going to be the same as the norm of my complex number. That the norm of complex number is just going to be the square root of a squared plus b squared. And then to find theta, notice how if I know a and b, so I know a and b and I want to find theta, I can then write theta, I can find theta because the tan of theta, if I know a and b, the tan of theta is going to be just b over a. So I can use these two things to find out what is my r and what is my theta when I want to write the polar form. So let me go back to my example down here. Now then, to find my r, the r is going to be just the norm of the complex number, which is the square root of 3 minus I, and that's going to be the square root of, let's say, square root of 3 squared plus negative 1 squared. So it's going to be the square root of the real part squared plus the imaginary part squared. And this is going to give me the square root of 4, which is 2. So now I have r. Now to find theta, I knew that tan of theta is going to be the imaginary part. Let me actually go back again. It's going to be the imaginary part divided by the real part. So my tan theta in this case is going to be negative 1 over 3. Negative 1 over square root of 3. Okay. So the tangent of what angle is square root of, is negative 1 over square root of 3? Well, the tangent of negative 30 degree, and the tangent of 150 degree is going to be negative 1 over square root of 3. But which one do I need to use? For this, you actually have to look at the picture that we see earlier. We can kind of see how the my complex number here, this is in the quadrant 4, it goes this way. So the angle that I'm looking for is going to be negative 30 degree. So that means the polar form for this guy is going to be r cis theta, and my theta is going to be negative 30 degree. It's going to be negative 30 degree. Or if I want to write this in polar form, that's going to be 2 cis of negative pi over 6. Okay, so that's my answer for part B. For my part C, 2i, well, this is rather simple. My 2i would be just here because, well, if I were to write this as in the usual form, that's going to be 0 plus 2i. So the coordinate for that is going to be just 0 and 2, and 0, 2 would be here. So this is my 2i. So notice how I is here, and then so 2i would be here. So that makes sense. Now this guy would have length 2, and then the angle between this guy and the positive x-axis is 90 degrees. So the polar form for this one is just going to be 2 cis of 90 degrees. Or we can write this as 2 cis of pi over 4 then.